Hello everybody. Let us start our discussion today. In the last about 15 lectures, we talked about special relativity, of particular formalism for the special relativity. We talked about geometries. We talked about certain properties of curved manifolds. And in the last lecture, we talked about the energy momentum tensor. Today is the day when it all comes together and we'll finally formulate or give prescription to how it works in general relativity, how you write down things in general relativity. And then we'll also have some time to discuss about certain concepts which we always used in our classical mechanics, the good old classical mechanics, and how the parallel to those comes about in general relativity. And these are some concepts that we'll use in the next 2 or 3 lectures, where we will finally have look at some of the applications of general relativity. So what is the prescription? So we have almost all the tools to write down the prescription, and there are certain things which I will not be able to prove for you in this short course, and there are certain things which I have not told or will not be telling you, but that's all right. What we learn does matter. The prescription is the following. What we want to do here is to do physics in presence of gravity. So what we want to do so basically the question we are asking is the following, that we have a physical law. How do I write down the equations a particle will follow in that physical law? Say the law is electrodynamics, for example, if I have gravity. Previously, gravity was a force, but as we have seen that it can be completely described in terms of the geometry of space-time. And we also saw that, okay, so if I say that how to do physics in presence of gravity, if it is a uniform gravitational field, it's nothing but an uniform acceleration. So equivalently say that we can also use this to look at things when there is a uniform accelerations. So coordinate transformation between reference frames, where previously we could do only uniform velocity, now we also know how to do with uniform accelerations. Now this is a question you are asking. So what is the answer? So how we do are the following. So first you have to find the physical law that you want to look at. So let's say find a physical law. This can be anything. Like for example, it can be the physical law of a force field free particle. The particle is supposed to move in a straight line. But that is not good enough. We not only have to find that physical law, write it in the covariant form. So I have to write it in the covariant form. Okay, one thing I forgot when I say, okay, so write it in a covariant form. So this physical law first you find in an inertial frame. So how do you write down this physical law in an inertial frame? That is what you do first. And as we have seen that any particle freely falling in gravity is in an inertial frame, local inertial frame. So we can do that even if we are in a gravitational field. But first you forget about any non-inertial effects. Go back to your good old inertial frame, and all of the laws that we know are know of are written down in the inertial frame. So write down the inertial physical laws there and write them in the covariant form in 4D Minkowski space, because that is the space we deal with in the inertial reference system. So this is essentially, you write down the law as you will write it down in special theory of relativity. So when I say covariant form, it basically means my laws are written in terms of tensor equations. That's what I mean by covariant form. Next, elevate to the general coordinate system. So what do I mean by elevate to a general coordinate system? I mean that, the gravity is there and it must be played, this entire thing in actually it is played in a gravitational field, and that gravitational field is described by G alpha beta, a metric. So whatever was your eta alpha beta in the Minkowski space, go from there and replace those with G alpha beta. Whatever was del alpha in your Minkowski space, wherever you have seen that, replace that by gradient of alpha. Or, I mean, I should not say gradient of alpha. So this is the covariant derivative essentially. So normal derivative goes to the covariant derivative, and eta goes to G. That's all that you have to do. Once you know G alpha beta, you can calculate what are the Christoffel symbols, and so that will tell you what is the covariant derivative, and that's it. So you write down the inertial form of the law in a covariant notation, change eta to G and del to covariant derivative, you get the law in any reference system. So this is what general relativity is telling you. But then there is a question that how do I know what is the metric, or what is all the forms of the metric? Now, just to remind you that when I say how do I know about G alpha beta, remember that metric is a symmetric second rank tensor which has 10 components. So these are, when I say how do I know about G alpha beta, how do I know these 10 functions? 10 functions that I want to know. So how do I know them? That is a question. Well, we got some clue and talked about it last time. We saw that, okay, the 0, 0 component of the metric is related to the phi, and the phi is related to the matter density with this expression. Last time also I forgot to write capital G, it came in the right hand side. One should write 4 pi capital G rho, but anyway. So we saw that this phi, grad square phi, the left hand side is like G alpha beta, the Einstein metric, and rho is the 0, 0 component of the energy momentum tensor. So now this I will not prove for you. If you use the Wickfield limit, that is the Newton's prescription of gravity, Newtonian gravity, one can actually write down how these two are related, and the answer is 8 pi g by c to the power 4 is a constant that sits in between these two. This is what I call, or what is called as, the Einstein's equation. Again, this you can consider as a first principle for the time being. There is no harm in doing that. If you take this as a first principle, the rest of the gravity follows. That is how it works. So T alpha beta is the source term, the energy momentum tensor. This is the source of gravity. Remember the components it has. It has energy momentum density, it has pressure and stress. So that is something new, because if you look at the Poisson equation over here, the source of gravity is solely given by the matter density, but now it is given by matter or energy density, but also momentum density, pressure and stress. So all of these determines what is the source for gravity. And the left hand side, this is the Einstein tensor. Remember that this is r alpha beta minus half, which is scalar g alpha beta. This is second derivative of the metric. Also has the first derivative, but second is the important thing. And you are solving for metric here, right? You are solving for the metric. So this equation, if I look at the Einstein equation, remember that g alpha beta is symmetric, so is t alpha beta. So Einstein equation has, so if I ask you how many independent equation does the Einstein equation have, it has 10 independent equations. And it looks so quite good that we wanted to solve for the 10 components of the metric, 10 functions. And I have these 10 differential equations because capital G alpha beta is second derivative of the metric. So it's a differential equation on 10 differential equations. I want to solve 10 components, 10 functions. It's absolutely fine. But actually not quite so, because I also have the Bianchi identities. Which is in this form if you write, so this equals to 0, right? Now if you look at this, it gives me 4 constraints. Why I say 4 constraints? Well, this is an identity, it's not an equation. This comes because of the form of G alpha beta. But and here beta is summed over, so there are essentially 4 of these identities. And so they serves as 4 constraints with the 10 components here, which means these are not 10 independent equations. Independent equation is 10 minus 4 equals 6. There is only 6 independent equations. And you realize then there is something wrong now, because I have 10 functions to solve for. So let us write it down here, it is important. So we understood that we have 10 functions G alpha beta to know we have 6 differential equations. So it is obvious that we will never be able to know what are these g alpha betas, these functions, all 10 functions, unless I by hand choose 4 conditions. So I need to hand pick 4 conditions to explicitly write g alpha beta in a given coordinate system. Right, so g alpha beta, remember we are writing down the components of the metric in a given coordinate system. That's what g alpha beta is. And we are saying that they are functions of the coordinates, of course. And what are these 10 functions that we want to solve? That I realize that I have to impose some handpicked conditions on the 10 g alpha betas, 4 such conditions, such that I can able to write down g alpha beta in that in that particular coordinate system. In different coordinate system, it can be different. So these 4 degrees of freedom are called 4 gauge freedoms. These are just like the gauge freedom you have in electrodynamics. If we discuss electrodynamics in the next semester, we'll probably talk about it there. But I guess that you already know about the gauge degrees of freedom in electrodynamics, which comes from the fact, by the way, that the charges are locally conserved. But anyway, so that's a different thing. But here we have 4 gauge freedoms in relativity, and this is essentially is coming because we are trying to find out the components of the metric in a given coordinate system. So I have a choice on that coordinate system, and the metric will look different if I choose a different coordinate system. It's all on that choice of the coordinate, and that coordinate choice is completely artificial. It's imposed by me to find the metric. Whatever coordinate choice you do, what will not change is the scalar curvature R. What will not change is the Einstein equation in this form. What will not change are the equations of the geodesics, which essentially mean that, well, I can choose a certain coordinate system for my convenience to write down these 10 functions we call the components of the metric, which is very convenient for me to work on, calculate separate different things. But it's that automatic gauge degree of choice I have ensures that the physical quantities, like the curvature of the space or the type of the space, geometry of the space, will never change. That's the gauge degree of freedom, is ensuring that. So you see that we have come to a very, very powerful theory which let you work on any coordinate system of your choice, but at the end of the day, the physical solutions will be meaningful. They will not depend on the coordinate systems. And that's all we wanted to start with. If you remember, our entire goal was to write down physical laws in a reference frame independent way. Then it does not depend on the observer who is writing down the physical law. Every observer will write down the physical law the exact same way. And if they do that, then they can figure out the consequences. I don't need to figure out separate physical laws for separate observers. That's all is done now in general relativity, in a general coordinate transformation. It was also done in special relativity, but only for inertial coordinate transformation. Now it's more general. All right. Let's look at some example. So let's see what we have done here. We said that we'll write a physical law in an inertial frame, write it in the covariant form in 4D Minkowski space, elevate it to general coordinate system by doing this. Okay. And how to know G alpha beta? So that is by solving the Einstein equation. Once somebody has told you, so this entire thing is the Einstein equation, not only T alpha beta obviously. Once somebody has told you what is T alpha beta, you can solve for Einstein equation. You can solve for G alpha beta by solving Einstein equation. So example, the prescription is very simple, not what comes out from the prescription. What happens most of the time is that you get equation but cannot interpret it. So we'll see that how it is something else that we will learn today will help us interpret things in general relativity, which we'll see in the next lecture probably. But let's see what are the examples. So first let us consider that we have a free particle. This we have done before, but let me go through it again. So for a free particle, so what is the equation of motion? Equation of motion in covariant form. And so this is in Minkowski space. I'm just writing in STR, special theory of relativity. So this is d u alpha d tau equals 0. Free particle, right hand side is 0 and u alpha is the vector. So this is 4 vector, you see. This is our knowledge of differential geometry coming in here. Tau is a free parameter, a parameter. In this case, it can be proper time, free massive particle. And that's it. So that's the differential equation. You can write this in a little elaborate form where you say that, okay, so this is dx beta, d tau, and then del u alpha del x beta equals 0. How do I, so this is already the Newton's first law essentially written in the covariant form. How do I write it in general coordinate? Very simple. What all I have to do is that, so this is, okay, so let me write it in a different form. So this is also u beta del u alpha del x beta, right? Because dx beta d tau is u. What all it will be that del x beta will change to the covariant derivative, and that's all. I have to also remember that the metric is the metric that you are interested in. So here if it is eta alpha beta, well, it comes here, it will become g alpha beta. So if I want to lower this index, for example, I have to multiply this equation from the left with g alpha beta. Let me just put one more thing. I can write this in a little different form. So I can multiply both sides by m. And if you remember that m u beta, I can write as the 4 momentum. So this equation, this was probably in one of your homework. Can also be written this way. Okay, which we'll be using later in today's lecture. Anyway, so this is the example of free particle. So I should not call this one. So let's call this A, free particle. First thing is that equation of motion. And the second thing is going to the general coordinates. So B is, say, electrodynamics. So what are the equations of electrodynamics? In electrodynamics, in covariant form, you define this tensor called f mu nu. This is called Maxwell's sorry, this is called Maxwell's tensor or field tensor. This has electric fields and magnetic fields. It's an antisymmetric tensor also. It's an antisymmetric tensor. And the equation of electrodynamics is this. There are mu 0 by 4 pi, I guess, the exact factor, but this can be, I don't remember exactly what it will be, but it's basically this. So this is the equation of electrodynamics. And there is one more equation where you write, so it's basically f mu nu alpha plus f alpha mu nu plus f nu alpha mu equals 0. This is an identity. This actually gives you the source-free Maxwell's equation. Divergence of B equals 0 and curl of B is curl of E is minus del B del T. So those two is there in this single thing, and there are 4 equations here. But anyway, 4 scalar equations here. But this is an identity. This is actually the Bianchi identity for electrodynamics. But so this is, I have written down electrodynamics, the first step, in the covariant form. How do I get the actual electrodynamics in curved spacetime? Well, as simple as this. And f, so I can write this now as semicolon alpha. So this is, remember that I have to anti-symmetrize the indices. This equals to 0. You see that the equation looks tremendously simple and the translation is tremendously simple. Once you try to solve things, it may become difficult. But that's it. So that's the entire prescription for doing general relativity. Let me put back one thing which we have not discussed yet. So let us go back to the Einstein equation, and I will call it a constant term. And we'll see why I put a big gap over here. You see, Einstein equation, which as I said, one can get that by using the Newtonian limit. Alright, so this is the Einstein equation. Interestingly, I am sorry, so we are in general coordinate. This is equal 0. That's the Bianchi identity. And remember that the prescription now tells us that, remember that I had in flat space T alpha beta this equals to 0. So that gave us all the fluid equations that I knew of. And how do I change that to the curved space time? Well, I just do this. And that will also be 0. And that's my prescription for general relativity. So what this equation is, I can also argue to this equation saying that, okay, so covariant derivative of g alpha beta is 0 and so is of t alpha beta. So I just integrate them, I get this equation. But you know that integration always comes with an integration constant. So I should also be writing an integration constant for this this equation, the Einstein's equation. So how should I write the integration constant? Well, you see, okay, by g by c to the 4 here, t alpha beta, I can write it in the left hand side or right hand side. There is something very interesting which happens if you write it in left and right hand side. But remember that the integration constant is an integration constant, which means that if I take the covariant derivative of that, it should also go to 0. And one thing we know of which the covariant derivative is 0, and that is g alpha beta. So this extra term that I get is, in this case, is a constant. It's essentially has to be a constant in this theory, and this does not have much effect if I don't go to the cosmological scale. So this only comes in handy, or it has a very small value in the present world. Because of that, only in the cosmological scales this becomes important. So this is called a cosmological constant. It has very interesting history why Einstein introduced it. He introduced it as an integration constant only, but why he introduced it, and later he thought that it is not a good idea. And in present day, after measuring things with very tedious observations, people have put back that term. So this is something real, and we will see when we do cosmology in the second example that we'll do in this course, the last example and also the second example, how this plays about. Now, as I said, that the equations here look very simple. So I have formulated Maxwell's electrodynamics in curved spacetime. It's amazing. So it's a very complicated theory. The equations look so much simple. So if I have some other tools, maybe while working out things, it will be easier for us to work out. Like if I want to work out the trajectory or some properties of this particular theory. And we know that what type of thing one looks at when you try to simplify things in a theory, and those things are called symmetries. So we'll talk in the rest of the lecture about symmetries of spacetime. Now, what is this thing that is describing our spacetime? The thing that is describing our spacetime is, of course, the metric. So this is also called the isometry of the metric. So this is the topic that we'll take up now. What do I mean by the isometry of the metric? So let's say I have a manifold here, and I have one local observer at that point, say A, another local observer at this point, say B. Okay. Now, going from A to B is essentially a coordinate transformation, because once I go to B, I will choose the origin at B, so it says that things for me becomes locally inertial. So if I follow a trajectory, I may follow a trajectory as I go from A to B. Now think of your original classical mechanics, good old classical mechanics. There we say that, okay, I am moving along this trajectory, and if the Hamiltonian is constant or the Lagrangian is constant, it is independent of time, then there is a conserved quantity which we call energy. So time was not a coordinate there, but if you think that way, so time is something which is conserved, giving me a conserved quantity called energy. So I am essentially translating in time and the energy is not changing. I can think of the same thing as for linear momentum. If my Lagrangian is independent of, say, the spatial component x, then the x momentum is conserved. So Lagrangian mechanics tells us this, that ddt of del L del X del Q dot Qi dot is the Pi dot, Pi. This is equals del L del Qi. So if Lagrangian is independent of the coordinate Qi, it does not depend on Qi explicitly, then the corresponding conjugate momentum is conserved. So can I formulate a similar thing in general relativity? And what I have to do here, I will go from A to B. I go to a nearby point, not so much different that I have just drawn them very much apart, and look at the world around me with B as my origin. If I see, so this is a particular translation I am doing from A to B, this particular type of coordinate transformation as I go from A to B. If I see that the metric locally at B is exactly the same as the metric locally at A, then I will say, imagine that I went to sleep while I was at A. I have measured the metric somehow at A, and while sleeping you take me to B, and when I wake up I measure the metric again around me to know if there is any change. Somebody has moved me and I don't find any change because the metric looks exactly the same, then I will not know that I have moved. So that is called a symmetry of the system. And what I am claiming is that with that symmetry there will be a conserved quantity. So that is what we are going to see now. Now what we are doing, so let's talk about a metric. So G alpha beta say. So this is a component of the metric. We are writing things in the component form. And these are functions of say x prime mu. Okay, so left hand side, let me write x mu, no prime. So this is just a convention. This and this goes to G, say, okay, it's all right. So let's call this prime. Say G mu nu, and see, I have a coordinate transformation. So this is here. This is at B, and this is at A. So at A, I call the coordinates as some mu. So what happens? Two things will happen. One is that the coordinate will obviously change because you're doing a coordinate transformation. The functions will also change. Remember that this is a second rank tensor. The functions will not remain same. The functions will change, and the functions will change in a very particular way. I'll be able to write down G mu nu as del x alpha prime del x mu del x beta del x nu G prime alpha beta. Just to remind you, these are function of x prime mu. These are function of, I'm sorry, mu. These are function of, so let me write a shorthand. These are function of x. These are function of x primes. Okay. So this is the general transformation rule. But if there is an isometry, then I will say that the metric functions remains the same, such that after waking up, looking or measuring the metric, I get no clue that somebody has shifted my position. But of course, if I have a point here and I put a, so I am measuring the metric from there, but I am measuring the metric at this point, say G. The position of G with respect to A and B will be different, that particular position. So I should be writing x prime here. And this happens when this is coordinate transformation is so what is the coordinate transformation I am talking about? I am saying that okay, so x alpha has changed to x alpha prime, but that is not very much. This is this plus some epsilon times xi alpha. Epsilon is very small. So there is an infinitesimal translation that I have given. The translation vector is xi alpha, and I want to see what happens to the metric. Now, one thing you will immediately notice is that del x prime alpha, del x mu, I can calculate now because I know what is x prime alpha in terms of the non-primed coordinates. So this will be delta alpha mu, del x alpha del x mu is delta alpha mu plus epsilon del xi alpha del x mu. Similarly, I can write for this term del x prime beta del x nu, that will be delta beta nu plus epsilon. And the metric now, what I want to do is I want to write this metric in terms of x. So g alpha beta x prime, I can express this in a Taylor expansion. So it's about x plus the little change from x to x prime, the little change is epsilon xi alpha times the derivative of the metric. So I should call it epsilon xi, some other index, sigma say. So the Lx sigma. And I can have higher order terms, but you see that epsilon is small, so I really don't need to keep up with the higher order terms. So what do I get? So I use these three expressions in this, and what do I get is g mu nu in the left hand side equals, let's see, when I use, so I will have 6 quantities, so let me write it down for you. So let's work this out. The first term is this delta, and g alpha beta. What will happen? Well, both the deltas has alpha and beta upstairs. So this g alpha beta will become g mu nu, which will eventually cancel with the g mu nu in the left hand side. Very nice. Plus, I take delta from here and this epsilon term from here and then this term. So which is order 1 in epsilon. So I will collect all the order 1 term in epsilon only. Now this delta alpha mu times g alpha beta makes it g mu beta, and I have delta xi beta del x nu here plus this, this, and the g again. Epsilon I have already taken out. Now delta beta nu with g alpha beta will change beta to nu, and I will get xi alpha del x mu here. What else do I get? Well, if I take these two terms, that's the alpha square term, which I will neglect obviously. The only alpha term that I can take is the two deltas and this term. So let's work that out. So epsilon again is outside, and in the g alpha beta will be replaced by alpha beta will be replaced by mu nu because of the two deltas. So what I get here is this, and then d mu nu del x sigma. Okay, so you see that this essentially whatever the curly bracket equals to 0 is what I get. So I can write this as the entire curly bracket equals to 0, but I want to do a little bit more. So let us start from the left hand side. So I have mu beta here. I forcefully add a term which starts with g mu beta, and then I add a gamma. This gamma is as if this was a total covariant derivative. So for that I need a eta nu here, and then xi eta. So I just add that forcefully. I do the same thing with this term, which is g alpha nu del xi alpha del x mu plus g alpha nu okay, forcefully I have done that. And then I have this term which is xi sigma del g mu nu by del x sigma. Because I have added this term forcefully, I also have to subtract. So let me do that. And let us do one more trick here. What I want is, I want to write it a little away such that I can put a bracket here. I'll see why I put a bracket. You see, the term I'm going to write down here is g mu beta Christoffel beta eta nu and xi eta. Eta where is a dummy index. So I could have used sigma for that. So I want to use sigma here. Because I have already used sigma for the xi which is outside, so I can take xi common if I use sigma here. So this will be sigma and nu. That's it. And what happens to this term? Well, xi I am already using sigma, so this is the Christoffel is alpha eta. Sorry, no eta. Instead of eta, I will get sigma, and then mu and g alpha nu. Okay, and this entire thing is equals to 0. Let's look at it. The first two, as it is constructed, is g mu beta covariant derivative with respect to nu of xi beta plus g alpha nu covariant derivative with respect to mu of xi alpha. And then I have xi sigma. Let's see what is this thing in the bracket. Well, it's a covariant derivative with respect to sigma of g mu nu. You can verify that. See that g mu nu, both the indices are downstairs. For that, the extra terms in the covariant derivative with Christoffel symbols comes with minus sign, and that's what we have got there. You can see that this will be equals to 0. So this verifies. And our metric is compatible, which means covariant derivative of metric is 0. So this goes to 0. And we get a very simple equation, which is the covariant derivative. And you see that this g can go inside because, again, the metric is compatible. So this I can write as simply as So beta, once it goes inside, so this becomes mu plus grad mu of xi nu equals 0. This equation has a name. It's called Killing equation. And these vectors are called Killing vectors. Let's revise how we have got this. We said that we are looking at a symmetry of the space-time, particularly the symmetry of the metric. The symmetry is such that if I do some transformation in the coordinates, the metric looks exactly the same. The components of the metric, the functional forms, are same as I change the metric. The function is a function of the new coordinates, but the functional forms are same. Now, for that, the type of transformation we are doing, we call this way, x alpha plus epsilon xi alpha. Now, this xi alpha is the transformation, and that transformation has to satisfy this equation, which we call the Killing equation. For that, there is a symmetry in the metric. So what? The metric has a symmetry on this. Is there a conserved quantity corresponding to this symmetry? Just like we saw that for time symmetry in the Lagrangian, there is an energy which is conserved, etc. Let's look at it. For that, we'll do some manipulations. So this is a question we are asking. So we start with the Killing equation. And when I say, is there a conserved quantity, what exactly we mean will be clear as we go along. Now, we realize that this is something symmetric. So I can, so this, if I interchange mu and nu, the whatever this left hand side of this equation is will never change. So what I can do is I can multiply this with p mu nu, p mu p nu, which is just happen to be the momentum for momenta. This is equals to still 0. But I want to add something to it. I want to add this term. You may say that how can you add something just like that? Well, what I add, if it is 0, then you will not complain. And I claim that this is 0. It's very simple to show that it is 0. this is symmetric in mu and nu, and now this is antisymmetric in mu and nu because of this minus sign. So if I change mu and nu, then this will pick up a minus sign, but this will not pick up a minus sign. So as we have seen earlier, they will add up to 0. So what I am doing all is adding a 0 to something which one should not complain about. But once we do that, what happens? The second term here gets cancelled out. So this equation now I can write as right. Let's add another 0 to it. Now to add another 0, we restrict our situation a bit. We say that we are looking at isometries of the metric. So let me write it down here because this is a point sometimes missed. We are looking at isometries of the metric while moving along a geodesic. What do I mean by that? Well, every freely falling observer in gravity is in his own geodesic. And what he is doing is he's looking at the nearby points. And he's trying to figure out if there is a symmetry in the spacetime. So as I am falling through the gravitational field freely, I try to look around and try to figure out if I have actually changed my position. If there is a symmetry, I'll never know that I have changed my position, right? So that is what is it about. So if there is a symmetry, then I can just add to this whatever expression I have here, the equation for a geodesic. And the geodesic, along the geodesic, we know that what is the equation for a geodesic. And the equation for a geodesic has the right hand side equals to 0. That is what we will exploit now. We'll say that I add to it, say, xi mu and p nu grad nu p mu. Let's see what it is. Well, this is the geodesic. That is supposed to be equals to 0, so I have just added 0. And why do I say it's a geodesic? It's written in terms of p. Well, that we have just said a little bit earlier and said we'll use it later. That a geodesic can be written this way. Okay, that's what I have used. And now what it becomes? Now something interesting happens. P nu stays as it is outside. But I can write this now as grad nu of p mu xi mu. Because if I want to break this, so this equals to 0, I can write, I am claiming, once I break this, the covariant derivative follows the Leibniz rule. So it will keep p outside and operate on xi, so that is this term, and then it will keep xi outside and operate on p, and that is this term. So this is absolutely fine. What I have here is a scalar. What this is saying is the covariant derivative of this scalar is 0 along the geodesic. You can get one step further. This statement is only here. I can take my m outside, so there are two m's. One is for this p nu, one is for p mu. I can take them out, and this will look like I really don't want to write p. Okay, let's write this as p. So I am taken 1. This is nothing but saying that d tau of this scalar is 0, which is, first of all, it's a coordinate independent statement. All our statements are, they're written in terms of covariant, but here particularly the derivative is with respect to scalar of a scalar. It's the most simplest derivative that you can have. And what it is saying is, along the geodesic, if you have a Killing vector, so if xi mu satisfies Killing equation, then like, for example, very simple case, if there is a translation invariance in x direction, which means that now x0 prime is equals x0 plus xi 0, and the corresponding xi mu is, say, 1 0 0 0, so will be xi mu. I really want to write this xi. What is the conserved quantity? Well, when I contract it with P, the only thing that I will get is P0, which is essentially energy. So you get back the old thing that x0 is the time component. If there is a isometry along the time component, there is a time-like Killing vector. It's a time-like Killing vector. Then the energy is conserved along the trajectory. Okay, so this is just a more general way of saying this, and it's again, the more important thing is that it's a coordinate independent way of saying it. You have to just solve the Killing equations. How do I know that? Okay, so what is the so much important about this equation? Well, there are a lot of things, but one important thing is that you can really solve this given a g, because g is hiding within that Christoffel symbols or the covariant derivative. So if I know the covariant, if I know the g, I know the covariant derivative, and then I can find out what are the Killing vectors. In practice, it's not so easy, but in principle, one can. The Killing vectors, let us look at the symmetries of space-time, and that's what we started with, right? Symmetries of space-time is what we call the isometry of metric. Now, if I again write down the Killing equation here, it's very easy to remember. How many components does it have? Well, you realize that it's a symmetric second rank tensor, so it has 10 independent components. in 4-dimension, of course. So if I consider dimensionality to be d, the number of equations I have in here is d into d plus 1 by 2. If d equals to 4, it's 4 into 4 plus 1, which is 4 into 5, 20 by 2 is 10. Right? If it is, okay, so you can figure out what it is if I change d to some other values. Now this is the maximum possible number of killing vectors. This is the maximum possible number of killing vectors. Maximum number of symmetries. One symmetry associated with one killing vector. Possible for this case. A space which has all the possible symmetries this is called a maximally symmetric space. And this is of great importance in GR because in such space some interesting things happen. First of all, in maximally symmetric space, which is what we are dealing with now, it doesn't mean that such a space cannot have curvature. It can have curvature, but the scalar curvature which is R, it is the Ricci scalar, this is constant. It does not depend on the coordinates everywhere. So there is only one number which specifies the scalar curvature. In general, it can be different at different places. But you see, if it is different at different places, that is one constant that you can measure. And if you measure it to be different at different places, then you can measure that and figure out that you are at different position in your manifold. If you can figure that out, obviously you are not in a maximally symmetric space. The symmetry is broken. The Riemann, which one like to write as say alpha, beta, mu, nu, in a maximally symmetric space is very simple. It is given by, and it's of say d dimension. It is given this way. Beta nu g alpha mu minus g. Okay, so this is a very simple form of this, and the Ricci is even simpler. Once you know this, you can get to this easily. And that R is a single number for the maximally symmetric space. Okay, so that is something that we'll be using later, the symmetries of this space-time. That's why I introduced it to you today. I'll stop there. Think about the maximally symmetric space a little bit. We may discuss about some examples in the discussion class. Thank you today. We have the full glory of general relativity in front of us. We are now ready to use them in real systems.